Hello everyone. The topic of my presentation is storage optimal control under net metering policies. This is a joint work with Arpan Mukhopadhyay and Abhishek, my supervisor, and Professor Elias. I'm very glad to have this opportunity to present in front of you as a semi-finalist for Pecan Street Student Research Competition. Before moving ahead to the problem, I would like to define net metering. Net metering facilitates bidirectional power flow to and from an end user. It encourages private investment in distributed generation. Net metering compensation can be bifurcated into two major categories: selling price being equal to the retail rate and selling price strictly lower than the retail rate. Arbitrage in general refers to buying a commodity when the prices are low and selling it when it is expensive. Now, in this process of buying and selling, because of the finite size of inventory or storage capacity or buffer, these actions are coupled in nature. So in terms of talking about energy storage arbitrage, if we choose to discharge the battery right now, then in future we have lesser amount of charge level to charge or discharge. So these actions are coupled in nature. Now an end user choose these actions in a certain way in order to make profit. The objective of this work is to find an efficient algorithm for optimal energy arbitrage. The proposed solution in this work basically discretizes a continuous optimization problem. We present a computationally efficient algorithm which is based on something defined as the subhorizons. So subhorizon is basically a portion of a big time horizon, and the threshold based structure of the optimal solution. Since we assume that these subhorizons are finite in time, and therefore we can say that optimal energy arbitrage is a finite horizon optimization problem. The proposed algorithm is dependent on accuracy of information. In real world, accurate information will not be available. We have to forecast quantities and there will be forecast errors. So how do we mitigate the effects of forecast error on arbitrage gains? We propose incrementally improving forecast model with model predictive control for mitigating the effect of forecast error on arbitrage gain. Uh, our system consists of a residential customer having a battery, a solar rooftop solar PV, and the consumer. This residential customer can supply power from the grid via energy meter and or extract power from the grid. Now the control decision that we have to decide on is what mode the battery should operate on in order to minimize the cost of consumption of this residential customer. The selection of mode of operation of the battery will depend on the future variations of price of electricity, solar generation, end user consumption level, and the battery charge level at the beginning of the time instant. We assume that electricity price vary over time. Each of these users act as price takers of electricity, and these consumers have non-elastic end user load. In terms of block diagram, we show the power flow directions and the associated variables of the system. The electricity prices can be separated as buying and selling. If the consumption is greater than zero, then the user is buying electricity from the grid, and vice versa for the selling case. The billable component of electricity will be sum of the end user consumption, renewable generation, and the storage output. Uh, the battery model that we use in the present work consists of two essential constraints: the energy constraint, which bounds the instantaneous energy of the battery within the maximum and the minimum bound, and similarly we have ramp rate constraint, which ensures that the battery do not charge or discharge beyond certain level, because that is not practical. We also consider the efficiency losses, which ensures that the change in the charge level and the output power are two different variables. For instance, we have to charge the battery, then we have to put extra amount of charge energy into the battery to compensate for the charging losses that the battery incur. The objective of optimization from an end user perspective is to minimize their cost of consumption over the time horizon. So the time horizon consists of n points, and so the net load, which will be the sum of renewable energy inelastic load of the consumer and the battery output. If that is positive, then the consumer is buying electricity from the grid, and vice versa for selling. We have the capacity constraints here, and the surge variable SI is bounded by as a function of the ramp rate constraint. We can see that these constraints and the search domain is linear and continuous in nature, and therefore it's convex. We have shown more in detail in our paper that the cost function associated here is indeed a convex function. So which ensures that we can use convex optimization tools to find the global minima. Uh, we list the Lagrangian of the optimization problem here as equation 3. We show that the existence of strong duality for our optimization problem, and using saddle point inequality condition, we propose a mechanism to find subhorizon. So consider this to be a time horizon in which we have n samples, and we say that these long huge time horizon can be subdivided into subhorizons, and the property of these subhorizons is the optimal action to choose the mode of operation, either to charge, discharge, or do something intermediate, will depend only on the parameters within the subhorizons. So the selection of the thresholds will be a function of only parameters within the subhorizon, and will be independent of all future and past subhorizons. So this makes it a finite horizon optimization problem. This optimal accumulated Lagrange multiplier mu star, which can be seen as from economic perspective as the shadow price of transaction, changes its value only when the battery capacity reaches to one of its boundaries, either B min or B max. So whenever the battery capacity is within these bounds, the shadow price remains constant. So in a subhorizon, we define subhorizon in terms of this shadow price or the optimal accumulated Lagrange multiplier, stating that the value of the shadow price remains constant in a subhorizon. We also mentioned that we explicitly list the threshold based structure of optimal decisions. So here in the first remark, case 1 list for the equal buying and selling price case, and the case 1 represents the lossless battery, and which has like 3 conditions here based on the price levels. So whenever the shadow price is less than the price at that instant, then the optimal action is to discharge. And similarly the other conditions, so there is a subgradient like structure whenever mu is equal to pi. When we consider battery efficiency losses, then we have 5 conditions, which is higher than the previous one, where there is no efficiency losses. And it becomes more complex for if we put additional condition on the buying and the selling price, which is listed here. And we can see that the conditions not only depend on the price levels and the efficiency values, but also on the net load without the storage component. So Zi represents the inelastic load, the sum of inelastic load and renewable generation. This is for the other side. The conditions written for the threshold based structure here. Based on these thresholds, we find an envelope like solution. So we have a lower bound and we have an upper bound. Now we need to find an optimal solution. So the second algorithm, which is mentioned more in detail in the paper, basically does find the unique solution. Suppose the envelope like structure is violating the lower capacity boundary, then we fix the last point at B min and backtrack to the starting of the subhorizon, and we say that this is the optimal decision. We showed that the worst case runtime complexity of the proposed algorithm is quadratic in terms of time instance for which in the subhorizon. So this is very efficient, computationally very efficient and very fast, which makes it very attractive for real-time implementation. Next, we describe a numerical result. The first plot here shows the electricity price in New York ISO. The second plot shows the user consumption, solar generation, and the grid supply. So basically the grid supply is the net load seen from the energy meter. Now, this is a case where there is no energy storage. Now we put energy storage into the system, and we force a constraint that the selling price is zero. So there is no incentive for the user to sell electricity. Now we can see that there was a negative net load, which implies that the solar generation was higher for certain time, and they were supplying back to the grid. Now, since there is zero selling price, instead of supplying back to the grid, the batteries are charging here. So it's more profitable for the battery to charge rather than sell at zero price to the grid. So the ramp rate constraints and the optimal ramp rate and the battery charge level for the same situation as in the previous slide is listed here. Um, Now, this we will in real time we will not have the accurate information. We'll have forecast errors. So, this arbitrage gain and the loss of opportunity from the end user perspective is very sensitive to the accuracy of forecast error. We can see that as the variance of the forecast error increases, basically the loss in opportunity that the consumer incurs because of inaccuracy of information is increasing. So it's like a linear function. So as the forecast model becomes bad and worse, the amount of loss or incentive that the user could make reduces. So how do we mitigate this? We propose incrementally improving forecast model along with model predictive control to mitigate the effects of forecast error. So this is a 2-month period simulation, and the red line in the back basically shows the ideal gains that the end user can make by performing arbitrage, and the blue and the black dots basically represents the actual gains which is being done by MPC plus adaptive forecasting. So we can see that the effects of inaccuracy of information can be aptly mitigated by incrementally improving forecast model plus model predictive control. With this, we would like to conclude our work. We presented a computationally efficient algorithm for energy arbitrage under net metering policies. We showed a threshold-based structure of the optimal solution based on the optimal accumulated Lagrange multiplier. These optimal accumulated Lagrange multiplier acts as shadow price of transaction. The optimal storage control decisions are dependent on prices, are independent of prices beyond sub-horizon, implying energy arbitrage as a finite horizon optimization problem. We also showed how that the mitigating effect of forecast error on arbitrage gain by using incrementally improving forecast model along with model predictive control. These are the major references that we have used in our present work. Thank you for your listening. Thanks.